So here's something to think about as you settle in tonight. Right now, wherever you are pinned to the surface of a ball of rock spinning at about 1,000 miles per hour at the equator, hurtling around a star at 67,000 miles per hour, which is itself drifting through a galaxy at hundreds of thousands of miles per hour. You feel none of it. You feel still. You feel like you're lying in a quiet room, gravity pressing you gently into the mattress, everything calm and steady and motionless. And for thousands of years, that feeling, that sense of being at rest on solid, unmoving ground, was all anybody had to work with. It was the starting point for every question anyone ever asked about how the world works. Why do things fall? Why does fire rise? What are stars? What holds the moon up? Why does a stone sink in water, but a ship made of stone floats? These are physics questions. They're the oldest questions in science. And the story of how people slowly, painfully, brilliantly answered them, that story is essentially the story of civilization learning to see past its own senses and discover that the universe is stranger, deeper, and more elegant than anyone standing on the ground could ever have guessed. And that's what we're going to walk through tonight, the whole history of physics. From the very first people who tried to explain the world without invoking magic, all the way to the edge of what we know right now. We'll take our time. We'll follow the people, not just the ideas, because physics is a deeply human enterprise, full of rivalries and obsessions, and lucky accidents, and stubborn geniuses who refuse to let go of a problem until it cracked. If you drift off somewhere along the way, that's completely fine. The universe has been running for about 14 billion years. It can wait while you sleep. Let's start where the story really starts, which is ancient Greece, roughly 2,500 years ago. Now, people everywhere in the ancient world thought about nature. The Babylonians tracked the stars with astonishing precision. The Egyptians understood geometry well enough to build pyramids. The Chinese and the Indians had sophisticated ideas about the elements and the structure of matter. But something happened in Greece around the 6th century BCE that was genuinely new. A handful of thinkers in the Greek colonies on the coast of what's now Turkey began trying to explain the natural world using reason alone, without relying on gods or myths or supernatural forces. They wanted to find the underlying principles, the rules, that governed everything. The first one we know about is Thales of Miletus, who lived around 600 BCE. Thales proposed that everything in the world was ultimately made of water. That's wrong, obviously, but that's not the point. The point is the type of claim he was making. He wasn't saying Zeus makes the rain, or Poseidon causes earthquakes. He was saying there's a natural substance, something you can observe and reason about, and it explains the structure of the world. That's a revolutionary move. That's the birth of natural philosophy, which is what they called physics for the next 2,000 years. After Thales came Anaximander, who proposed that the fundamental substance wasn't water, but something more abstract. He called the apeiron, the indefinite, the unlimited. Then Anaximenes said it was air, and everything was formed by air being compressed or rarefied. Then Heraclitus said everything was fire. That change itself was the fundamental reality, that you can't step in the same river twice. These guys disagreed with each other constantly, but they were all playing the same game, trying to find the one thing, the basic principle that underlies the bewildering variety of the world. And then came Democritus, around 460 BCE, and he had an idea that turned out to be so far ahead of its time, it's almost spooky. Democritus proposed that everything, air, water, stone, flesh, stars, is made of tiny, indivisible particles he called atoms. Atomos, in Greek, means uncuttable. He said these atoms move through empty space. They come in different shapes and sizes. They hook together in different combinations. And that's what makes the different materials we see. There's no mystical life force, no divine substance, just atoms and void. That's it. Think about what that is. That is, in essence, the correct answer. It would take more than 2,000 years for anyone to prove it, and the details are far richer and stranger than Democritus imagined. But the core insight, that matter is made of indivisible particles moving through space, that's the foundation of modern physics and chemistry. And he got there by pure reasoning, sitting in a Greek colony in Thrace, with no microscopes, no instruments, no experiments in the way we'd recognize them, just thinking. But the person who cast the longest shadow over ancient physics wasn't Democritus. It was Aristotle, born in 384 BCE in Stagira, in northern Greece. Aristotle was a student of Plato, who was a student of Socrates, so the intellectual pedigree is about as good as it gets. Aristotle was one of those minds that simply could not stop categorizing things. He wrote about everything: logic, ethics, politics, biology, poetry, rhetoric, metaphysics, and, crucially for us, physics. His book, literally called Physics, was the most influential work of natural philosophy in Western history. It shaped how people thought about motion, matter, change, and the structure of the universe for nearly 2,000 years. And a lot of it was wrong. Not all of it. Aristotle was a careful observer and a brilliant thinker, and many of his insights about biology, logic, and causation were genuinely profound. But his physics had fundamental problems, and the reasons it went wrong are worth understanding, because they tell you something important about why physics is so hard, and why it took so long to get right. Aristotle believed in a universe of purpose. Everything has a natural place, and it moves toward that place unless something interferes. Heavy things, like rocks and water, have their natural place at the center of the universe, which he thought was the center of the earth. Light things, like air and fire, have their natural place upward, toward the heavens. So a rock falls because it's seeking its natural place. Smoke rises because that's where fire-like things belong. It's a very intuitive framework, actually. It matches everyday experience pretty well. You drop a rock, it falls. You release a flame, the heat rises. Makes sense. But there are problems. Big ones. Think about a thrown ball. You throw a ball sideways. What keeps it going after it leaves your hand? According to Aristotle, things only move when something is pushing them. The natural state of an earthly object is to be at rest. So once the ball leaves your hand, what's doing the pushing? Aristotle's answer was that the air rushes around behind the ball and pushes it forward, which is, well, not great. It's a clever attempt, but it doesn't really hold up if you think about it carefully, and it would take about 2,000 years for someone to clearly articulate why. Aristotle also believed that heavier objects fall faster than lighter ones. A big rock falls faster than a small rock, in proportion to their weights. This seems intuitively right, and in everyday experience, where air resistance complicates things, it sort of looks true. A feather falls slower than a hammer, right? But that's because of air resistance, not because of anything fundamental about gravity. In a vacuum, the feather and the hammer fall at exactly the same rate. We know this. Apollo 15 astronaut Dave Scott actually did the experiment on the moon in 1971, dropping a hammer and a feather simultaneously in the lunar vacuum, and they hit the ground at the same time. But nobody had access to a vacuum in ancient Greece, and Aristotle's intuition led him astray. The thing about Aristotle, though, is that his authority was so enormous so deeply embedded in the intellectual culture of the Western world, especially after his works were integrated into Christian theology by Thomas Aquinas in the 13th century, that questioning him felt almost like questioning reality itself. For nearly 2 millennia, if you wanted to understand how the world worked, you started with Aristotle. And if your observations didn't match Aristotle, most people assumed the observations were wrong. But even during those 2 millennia, there were cracks. There were people who pushed back, people who noticed things that didn't fit. In the Islamic Golden Age, roughly the 8th through the 14th centuries, scholars working in Baghdad, Cairo, Cordoba, and across the Islamic world preserved, translated, and extended the Greek texts, and some of them went significantly further. A thinker named John Philoponus, actually a late antique Christian scholar in 6th century Alexandria, challenged Aristotle's theory of motion directly. He argued that when you throw a ball, you impart to it a kind of internal force. He called it an impetus, that keeps it moving even after it leaves your hand. The air doesn't push it. The ball carries something with it. This impetus theory was picked up and refined by Islamic scholars like Ibn Sina, known in the West as Avicenna, and later by the medieval European scholar Jean Buridan at the University of Paris in the 14th century. Buridan's version of impetus theory was actually pretty close to what we'd eventually call momentum. He was getting warm. And then there was Ibn al-Haytham, known in the West as Al-Hazan, who lived in Basra and Cairo around the year 1000. Al-Hazan is one of the most remarkable figures in the history of science, and he doesn't get nearly enough credit in popular accounts. He wrote a massive book on optics, the Kitab al-Manazir, the Book of Optics, that fundamentally changed how people understood vision and light. Before Al-Hazan, the dominant theory, going back to the Greeks, was that vision worked by rays shooting out of your eyes and touching objects. Al-Hazan showed that this was backwards. Light comes from sources like the sun or a flame, bounces off objects, and enters your eyes. He demonstrated this through careful experiments with pinhole cameras, with reflections, with the refraction of light through curved surfaces. He described the anatomy of the eye with surprising accuracy, and his methodology, forming hypotheses, testing them with controlled experiments, revising based on results, was remarkably modern. Some historians call him the first true scientist, and while that's always a debatable claim, it's not an unreasonable one. So the pieces were being gathered, slowly, over centuries. Impetus theory was chipping away at Aristotle's ideas about motion. Al-Hazan was demonstrating the power of experimental methods. The medieval universities of Europe, particularly Paris and Oxford, were producing scholars who were doing real physics. The Merton School at Oxford figured out the mean speed theorem for uniformly accelerated motion in the 1330s, which is essentially a kinematic equation you'd still use in a physics class today. The ground was being prepared, and in the early 16th century, a quiet Polish clergyman was about to set the stage for the biggest intellectual revolution in human history, not by studying motion on the ground, but by looking up at the sky and asking a question so dangerous that it would reshape everything. His name was Nicolaus Copernicus, and the question was this: what if the Earth is not the center of the universe? What if the Earth moves? Now, let's talk about what was happening with the sky during all of this, because astronomy and physics have always been deeply intertwined, each one pushing the other forward. The geocentric model of the universe, Earth at the center, everything else orbiting around it, had been the dominant view since Ptolemy formalized it in the 2nd century CE. Ptolemy's model was actually quite clever. It used a system of circles upon circles, called epicycles, to account for the apparent backward motion of the planets as seen from Earth. And it worked, in the sense that it could predict where the planets would be in the sky reasonably well. It just wasn't true. Copernicus published his great work, De Revolutionibus, in 1543, literally on his deathbed. Legend has it that a copy of the finished book was placed in his hands on the day he died. In it, he proposed that the Earth and the other planets orbit the Sun, not the other way around. Now, the idea wasn't entirely new. Aristarchus of Samos had suggested a sun-centered universe back in the 3rd century BCE, but Copernicus worked out the mathematics in detail, showing that a sun-centered model could explain the observed motions of the planets with geometric elegance. It wasn't immediately accepted, and Copernicus himself was cautious about claiming it described physical reality. The book's preface, added by a Lutheran minister named Andreas Osiander, without Copernicus's knowledge, suggested the model was merely a mathematical convenience, a way to simplify calculations. But the idea was out there now, and it was about to find its champion, Galileo Galilei, born in Pisa, Italy, in 1564. And Galileo is where modern physics truly begins. Not because he was the first person to do experiments. Alhazen was doing that 500 years earlier, but because Galileo combined experimental observation with mathematical reasoning in a way that nobody before him had quite managed, and he did it with a combative brilliance that made him impossible to ignore. Here's the thing about Galileo. He didn't just observe the world, he interrogated it. He set up controlled experiments. He rolled balls down inclined planes with exquisite care, timing them with water clocks and his own pulse, and he discovered something that Aristotle had gotten fundamentally wrong. Heavy objects and light objects, ignoring air resistance, fall at the same rate. Not approximately the same rate, exactly the same rate. The famous story about Galileo dropping 2 different weights from the Leaning Tower of Pisa is probably apocryphal. There's no reliable contemporary account of it happening. But the underlying physics he demonstrated through his inclined plane experiments is absolutely real. He showed that the distance a falling object covers is proportional to the square of the time elapsed. That's the law of free fall, and it's one of the first precise mathematical laws ever established through experiment. But Galileo did something even more important, something more subtle and far-reaching. He articulated the principle that would eventually become Newton's first law of motion. Galileo argued that the natural state of a moving object isn't rest, as Aristotle had claimed. If you could eliminate all friction, all resistance, a moving object would keep moving forever, in a straight line, at constant speed, indefinitely. No pushing required. The ball doesn't need the air rushing behind it. Once it's moving, it just keeps going, unless something stops it. This is the principle of inertia, and it is a complete reversal of Aristotle's physics. Aristotle said, motion requires a continuous cause. Galileo said no. It's not motion that requires explanation. It's changes in motion. Speeding up, slowing down, changing direction. Those require a cause. The motion itself just is. Think about how radical that is. For 2,000 years, the smartest people in the world had assumed that you need a reason for things to move. Galileo said you need a reason for things to stop. And he was right. That single insight, more than anything else, is the foundation on which all of classical physics is built. And then, Galileo pointed a telescope at the sky, and everything changed again. He didn't invent the telescope. That was Hans Lippershey in the Netherlands, probably around 1608. But Galileo built his own improved version in 1609, and he was the first person to use it systematically for astronomy. And what he saw demolished the Aristotelian cosmos. He saw that the moon had mountains and craters. It wasn't a perfect celestial sphere. He saw that Jupiter had moons orbiting it, proof that not everything orbits the Earth. He saw that Venus went through a full set of phases, like our moon, which only makes sense if Venus orbits the Sun, not the Earth. He saw sunspots, dark blemishes drifting across the face of the Sun, challenging the idea that the Sun was perfect and unchanging. He even observed that the Milky Way, that faint band of light across the night sky, was made up of countless individual stars, too faint to see with the naked eye. The universe was suddenly much, much bigger than anyone had imagined. Each observation was a nail in the coffin of the old worldview, and Galileo published them eagerly, eloquently, in Italian rather than Latin so ordinary educated people could read them. This brought him into direct conflict with the Catholic Church, which had incorporated Aristotelian cosmology into its theology. The Earth was the center because God made it the center. Humanity was special because its home was special. Challenging that arrangement was theologically dangerous. In 1616, the Church declared the heliocentric model formally heretical. Galileo was warned to stop promoting it. He more or less complied for a while, but in 1632 he published the Dialogue Concerning the Two Chief World Systems, which was technically a balanced presentation of both sides, but was transparently a demolition of the Earth-centered model. The character defending the old view was named Simplicio, which, come on, that's not subtle. The Pope, who had previously been friendly to Galileo, was furious. Galileo was hauled before the Inquisition in 1633, found guilty of suspicion of heresy, and sentenced to house arrest for the rest of his life. He was 69 years old. But here's the thing. They could silence the man, but they couldn't silence the physics. During his house arrest, blind and aging, Galileo wrote what many consider his greatest scientific work, The Two New Sciences, published in 1638, smuggled out to a publisher in Leiden. In it, he laid out the foundations of mechanics and the science of materials, the laws of falling bodies, the parabolic trajectory of projectiles, the analysis of beams and their breaking strength. This is where modern physics lives, in the marriage of careful experiment and precise mathematics, applied to how real things actually behave. There's a beautiful coda to the Galileo story. Johannes Kepler, the German astronomer who worked out the precise mathematical laws of planetary motion using the painstakingly accurate observations of Tycho Brahe, was a contemporary of Galileo's, and their work fit together like puzzle pieces, even though they approached science from very different temperaments. Kepler was mystical, almost obsessive about finding cosmic harmonies in the data. He tried for years to fit the planetary orbits into a model based on nested Platonic solids. He really believed God had designed the solar system as a geometric masterpiece. It's a beautiful idea, and it's completely wrong. But in the process of pursuing it, Kepler discovered something far more important and far stranger than what he was looking for. He found that planets orbit in ellipses, not circles. That was his first law. His second law says they sweep out equal areas in equal times, meaning a planet moves faster when it's closer to the Sun and slower when it's farther away. His third law connects the orbital period to the distance from the Sun with a precise mathematical relationship. These laws were purely descriptive. Kepler had no idea why the planets moved this way. He just knew they did, because the data said so, and it would take another giant to explain the why. Galileo died in 1642, still under house arrest. And in that same year, on Christmas Day, in a farmhouse in Lincolnshire, England, a premature baby was born, so small that, as his mother later said, he could have fit inside a quart mug. Nobody expected him to survive. His name was Isaac Newton, and he would take everything Galileo had started and build it into the most comprehensive, most powerful, most beautiful scientific framework the world had ever seen. Newton's story is fascinating, partly because he was such an unlikely character for the role. He was born into a farming family, his father dead before he was born, raised largely by his grandmother after his mother remarried and left him behind. He was solitary, secretive, obsessive, vindictive, and possibly the most naturally gifted mathematical mind in human history. He went to Cambridge in 1661 as an unremarkable student, but when the university closed in 1665 and 1666 due to the plague, Newton went home to the family farm in Woolsthorpe and had what might be the most productive isolation period in the history of thought. During those 2 years, working alone, he developed calculus, discovered the composition of white light using prisms, and began formulating his theory of gravity. All of it, in his mid-20s, at a farmhouse, during a pandemic. Let's talk about the gravity part, because the legend is so famous that people sometimes miss how genuinely remarkable the actual thinking was. The story about the apple falling on Newton's head is probably embellished. What Newton himself later said was that he saw an apple fall, and it set him wondering whether the force that pulled the apple down might be the same force that kept the moon in its orbit. That's the key insight. Not just that things fall, everybody knew things fall, but that the force making an apple fall and the force governing the moon's motion might be one and the same thing. That the physics of heaven and the physics of earth, which Aristotle had insisted were completely different domains governed by different rules, might actually be identical. Here's how Newton's reasoning went. The moon is orbiting the Earth, which means it's constantly changing direction. Changing direction means it's accelerating, even though its speed is roughly constant. Acceleration requires a force, so something is pulling the moon toward the Earth. Meanwhile, an apple falls because something pulls it toward the Earth. What if it's the same something? What if gravity, the force that pulls the apple, extends all the way to the moon, getting weaker with distance but never disappearing entirely? Newton worked out the mathematics. He figured out that if gravity decreases with the square of the distance, if you double the distance, the force drops to 1/4. Then you get exactly the right orbital period for the moon. And then he took it further, much further. He showed that this same inverse square law of gravitational attraction, applied between any two masses in the universe, could explain Kepler's 3 laws of planetary motion. Johannes Kepler, working from the phenomenally precise observations of the Danish astronomer Tycho Brahe, had discovered in the early 1600s that planets orbit in ellipses, not circles, and that they sweep out equal areas in equal times, and that there's a precise mathematical relationship between the orbital period and the distance from the Sun. But Kepler had described these laws without explaining them. He knew what the planets did, but not why. Newton's gravity explained why. One force, one equation, and the entire solar system falls into place. This is what Newton published in 1687 in the Principia Mathematica, which is almost certainly the most important scientific book ever written. In it, he laid down 3 laws of motion that still form the foundation of classical mechanics. The first law, an object at rest stays at rest, and an object in motion stays in motion at constant velocity, unless acted upon by a force. That's Galileo's inertia principle, stated with crystalline precision. The second law, force equals mass times acceleration. F equals ma. That's the equation that lets you calculate anything. The trajectory of a cannonball, the stress on a bridge, the acceleration of a rocket. It connects cause, force, to effect, acceleration, through the property of the object, mass. It's simple, it's universal, and it's one of the most powerful equations in the history of science. The third law: for every action, there is an equal and opposite reaction. You push on the ground pushes on you. A rocket pushes exhaust gases backward. The gases push the rocket forward. Every force comes in pairs. And then, on top of these three laws, Newton placed his law of universal gravitation. Every mass in the universe attracts every other mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Every mass, not just planets and apples. Your body is gravitationally attracting the walls of this room right now. The force is absurdly tiny, but it's there. Gravity is universal. That word, universal, was new. Before Newton, nobody had seriously proposed that the same physical law could apply everywhere, to everything, at all scales. That's the revolution. That's what made Newton, Newton. Now, to do all of this, Newton needed mathematics that didn't exist yet. The problems he was solving: how objects move when forces change continuously, how to calculate the area under a curve, how to describe quantities that are changing at every instant. These required a new kind of math. So Newton invented it. He called it the method of fluxions. We call it calculus. And here's the thing about calculus. It's not just a tool for physicists. It's the language of change. Anytime something is varying, growing, shrinking, accelerating, flowing, oscillating, calculus is how you describe it precisely. It's the mathematical backbone of engineering, economics, biology, and virtually every quantitative science. Newton invented it essentially as a side project, as a tool he needed to solve his physics problems. And he barely published it. He sat on it for decades, sharing his methods only reluctantly, which is part of what fueled the ferocious priority dispute with Leibniz later on. And the framework worked. It worked spectacularly. Using Newton's laws, you could predict the motions of the planets, the trajectories of comets, the tides of the oceans, the paths of cannonballs, the vibrations of strings. You could calculate things that hadn't been observed yet, and then go look for them and find them exactly where the math said they'd be. In 1846, more than a century after Newton's death, astronomers discovered the planet Neptune by pure calculation. They noticed tiny irregularities in the orbit of Uranus, worked out where an unseen planet would have to be to cause those irregularities using Newton's gravitational equations, pointed a telescope at that spot, and there it was. That's the power of Newtonian physics. You can predict the unseen. Newton was celebrated, knighted, made president of the Royal Society, eventually buried in Westminster Abbey. But he was also, by many accounts, an extremely difficult person. He feuded bitterly with Robert Hooke over who deserved credit for the inverse square law of gravity. He fought with Gottfried Wilhelm Leibniz over who invented calculus, a dispute that was so vitriolic it damaged scientific collaboration between England and continental Europe for generations. Both Newton and Leibniz had developed calculus independently, but Newton was convinced Leibniz had stolen his ideas, and he used his influence as president of the Royal Society to stack the committee that investigated the matter. The committee, unsurprisingly, ruled in Newton's favor. It wasn't Newton's finest moment, but the physics transcended the person. By the 18th century, Newtonian mechanics was the undisputed framework for understanding the physical world. The universe was a vast clockwork, governed by precise mathematical laws. If you knew the positions and velocities of all the particles in the universe at any given moment, and you had enough computing power, you could in principle calculate the future forever. This idea, later articulated most clearly by the French mathematician Pierre-Simon Laplace, is sometimes called determinism, and it was deeply satisfying. The universe was knowable. It was predictable. It was mechanical. And for about 200 years, that picture held. Newtonian mechanics was refined, extended, reformulated in elegant new mathematical frameworks by giants like Leonhard Euler, Joseph Louis Lagrange, and William Rowan Hamilton. But the core ideas didn't change. Force, mass, acceleration, action and reaction, gravity as an inverse square law. The clockwork universe ticked along, and physics seemed, to many, essentially complete. There were details to fill in, but the grand architecture was done. Except it wasn't. Because alongside mechanics, a completely different branch of physics was growing, driven not by falling apples and orbiting planets, but by something much more practical, the desire to build better engines. And this branch, the science of heat, would eventually lead to some of the deepest and most unsettling ideas in all of physics. Ideas about energy, disorder, and the fate of the universe itself. And the thing that started it all was the remarkably simple question of how to get more useful work out of a steam engine. The steam engine had been around in practical form since Thomas Newcomen built one in 1712 to pump water out of coal mines. James Watt improved it dramatically in the 1760s and 1770s, adding a separate condenser that made it far more efficient. The Industrial Revolution was underway, powered literally by steam, and the question of how to squeeze more work out of each pound of coal wasn't just academic. It was economic. It was competitive. It was the difference between a profitable factory and a bankrupt one. And in 1824, a young French military engineer named Sadi Carnot published a small book that would become one of the most important works in the history of physics. Carnot was only 28, and he died just 8 years later of cholera, so he never saw the impact of his ideas. But the book, called Reflections on the Motive Power of Fire, asked a deceptively simple question. Is there a fundamental limit to how efficient a heat engine can be? Can you build an engine that converts all the heat energy from burning coal into useful work? Or is there some unavoidable waste? Carnot showed that there is a limit, and the limit depends only on the temperatures involved, the temperature of the hot source where the heat comes from, and the temperature of the cold sink where the waste heat goes. No matter how cleverly you design your engine, you can never convert all the heat into work. Some must always be wasted. This is a fundamental law of nature, not an engineering limitation. You can't cheat it. You can't work around it. It's built into the structure of the universe. Now, Carnot didn't know exactly why this was true. His theoretical framework was partly wrong, because he thought heat was a fluid that was conserved, an idea called caloric theory that turned out to be incorrect. But his conclusion was right. And over the next few decades, a series of physicists would build on his work and establish what we now call thermodynamics, the science of heat, energy, and their transformations. Lord Kelvin, William Thomson, who was one of the towering figures of 19th century physics, helped formalize many of these ideas and gave us the absolute temperature scale that bears his name. Kelvin recognized that Carnot's limit implied a fundamental direction to natural processes, a one-way character to the flow of energy that hinted at something deep. But before all of that could be properly sorted out, there was a more basic question to resolve. What even is heat? Is it a substance, a fluid, or something else? The first great clarification came from James Prescott Joule, a brewer's son from Manchester, England. Joule was wealthy enough to pursue science as a hobby, and he was meticulous to an almost obsessive degree. He performed a series of exacting experiments in the 1840s, showing that mechanical work could be converted into heat and heat into mechanical work at a fixed, measurable exchange rate. This was a direct challenge to the caloric theory, because if heat were a conserved fluid, you couldn't create more of it by doing mechanical work. Joule showed you could. He used falling weights to spin paddles in water and measured the tiny temperature increase. He found that a specific amount of mechanical work always produced the same amount of heat. Energy wasn't being created or destroyed. It was being transformed from one form to another. This is the first law of thermodynamics. Energy is conserved. You can transform it, from mechanical energy to heat, from heat to electrical energy, from chemical energy to light. But you can never create it from nothing, and you can never destroy it. The total energy of an isolated system stays the same, forever. It's one of the most fundamental principles in all of physics, and it applies to everything, from the chemistry of your cells, to the burning of stars, to the expansion of the universe itself. But Carnot had shown that even though energy is conserved, you can't convert all of it into useful work. There's always waste, and understanding that waste, understanding why the universe doesn't just recycle its energy perfectly, leads to the second law of thermodynamics, which is, in many ways, the most profound and unsettling law in all of physics. The person who articulated it most clearly was a German physicist named Rudolf Clausius, working in the 1850s and 1860s. Clausius introduced a concept he called entropy, from the Greek word for transformation, and he stated the second law in a way that sounds almost like a philosophical declaration. The entropy of the universe tends to a maximum. In simpler terms, the second law says that in any spontaneous process, the total disorder of a system and its surroundings increases. Heat flows from hot to cold, never from cold to hot, on its own. A cup of coffee cools down. It never spontaneously heats up by absorbing heat from the cooler room around it. A dropped egg splatters. It never spontaneously unsplatters. These aren't just practical observations. They're expressions of a deep statistical truth about how energy and matter tend to spread out, to distribute themselves more evenly, to move from ordered arrangements to disordered ones. And here's the thing that makes the second law so haunting. It implies a direction to time. The laws of mechanics, Newton's laws, are perfectly reversible. A movie of billiard balls bouncing off each other looks just as physically valid played forward or backward. But the second law breaks that symmetry. Entropy increases. Things run down. The universe is heading, slowly, inexorably, toward a state of maximum entropy, a state of perfect, featureless equilibrium where nothing interesting happens anymore. The physicist, Lord Kelvin, called this the heat death of the universe, and it remains, as far as we know, the ultimate fate of everything. The stars burn out, the galaxies disperse, the black holes evaporate, and eventually, in some unfathomably distant future, the universe is just a faint, cold, uniform glow of radiation, drifting toward absolute zero. Not with a bang, but with a whimper. And this brings us to one of the most remarkable figures in the history of thermodynamics, Ludwig Boltzmann, an Austrian physicist who, in the 1870s and 1880s, provided the microscopic explanation for entropy. Boltzmann showed that entropy is a statistical quantity. It measures the number of different ways the atoms and molecules of a system can be arranged while still looking the same from the outside. A shuffled deck of cards has higher entropy than a sorted one because there are far more ways the cards can be arranged in a disordered state than in a sorted one. Similarly, a room where the air molecules are evenly distributed has vastly more possible microscopic arrangements than a room where all the molecules are bunched in one corner. Systems tend toward high entropy simply because there are overwhelmingly more high-entropy states than low-entropy ones. It's not a force pushing things toward disorder. It's pure statistics. It's the universe playing the odds. Boltzmann expressed this insight in a beautiful equation. S equals K log W. Entropy equals Boltzmann's constant times the natural logarithm of the number of microstates. It's carved on his tombstone in Vienna, and it's tragic that it had to be a tombstone. Boltzmann's statistical approach was attacked relentlessly during his lifetime by physicists who didn't believe in atoms, particularly Ernst Mach and Wilhelm Ostwald. Boltzmann suffered from depression, and in 1906, while on holiday with his family in Trieste, he hanged himself. He was 62. Within a few years, Einstein's work on Brownian motion and Perron's experiments had vindicated everything Boltzmann had argued. The atoms he believed in were shown to be real, and his statistical mechanics became one of the foundations of modern physics. He didn't live to see it. That's heavy. Let's come up for air and talk about something more immediate, something you interact with every single day without thinking about it. Electricity and magnetism, and the story of how two seemingly unrelated phenomena turned out to be aspects of the same underlying reality. A story that rivals Newton's unification of earthly and celestial gravity for sheer intellectual beauty. People had known about electricity and magnetism for thousands of years, in the way that ancient people knew about most things, as strange, isolated curiosities. The Greeks noticed that rubbing amber with fur made it attract light objects. They noticed that certain rocks, lodestones, attracted iron. But these were parlor tricks, oddities. Nobody connected them. Nobody imagined they might be related. Nobody suspected that they were, in fact, two faces of the most important force in your daily life, the force that holds your atoms together, that makes chemistry possible, that carries the light to your eyes and the signals through your nerves. But progress was being made on multiple fronts. Benjamin Franklin, in the 1750s, had famously shown that lightning is electrical, and his work on positive and negative charges laid the groundwork for understanding how electricity behaves. Charles Augustin de Coulomb measured the force between electric charges with exquisite precision, finding that it follows an inverse square law just like gravity: double the distance, quarter the force. Alessandro Volta built the first true battery in 1800, providing a steady source of electric current for the first time. And then André-Marie Ampère, a French physicist, did foundational work on the relationship between electric currents and the magnetic forces they produce. But the person who truly connected electricity and magnetism was Hans Christian Ørsted, a Danish physicist. In 1820, during a lecture demonstration, and this part is wonderful, he happened to notice that when he turned on an electric current near a compass, the compass needle swung. Current flowing through a wire was producing a magnetic effect. It was almost accidental. Ørsted hadn't been looking for it, but he recognized what he'd found, published his result, and it hit the physics community like a thunderbolt. If electric currents produce magnetism, could magnetism produce electricity? The hunt was on. The person who answered that question, and who contributed more to our understanding of electromagnetism than anyone except one man, was Michael Faraday. And Faraday's story is one of the most improbable and inspiring in the history of science. He was born in 1791 in South London, into a poor family. His father was a blacksmith. Faraday had almost no formal education. He left school at 14 and was apprenticed to a bookbinder, but he read voraciously, especially books about science, and he attended public lectures at the Royal Institution whenever he could. In 1812, at the age of 20, he attended 4 lectures by the famous chemist Humphrey Davy, took meticulous notes, bound them beautifully, he was a bookbinder after all, and sent them to Davy, along with a letter asking for a job. Davy hired him as a laboratory assistant, and that was the beginning of one of the greatest scientific careers in history. Faraday was not a mathematician. He never learned calculus, never worked with equations the way the continental physicists did. But he had an extraordinary physical intuition, a gift for designing experiments, and a visual way of thinking about forces and fields that turned out to be more profound than anyone realized at the time. It was Faraday who introduced the concept of the field, the idea that a magnet or an electric charge doesn't just exert a force on distant objects through empty space, but creates a condition in the space around it, a field that extends outward in every direction and exerts force on anything that enters it. He visualized these fields as lines of force, fanning out from magnets and charges, and he spent years mapping them, using iron filings and compass needles, and his own remarkably precise instruments. In 1831, Faraday discovered electromagnetic induction, the principle that a changing magnetic field produces an electric current. Move a magnet through a coil of wire, and current flows. Stop the magnet, and the current stops. It's the changing that matters, not the static presence. This is the principle behind every electrical generator on Earth. Every power plant, coal, gas, nuclear, hydroelectric, wind, works by spinning magnets inside coils of wire, or coils of wire inside magnets, converting mechanical energy into electrical energy through Faraday's induction. The lights in your room right now, the electricity flowing through the wires in your walls, it all traces back to a principle discovered by a bookbinder's apprentice in 1831. Faraday also discovered the laws of electrolysis, the magneto-optical effect, diamagnetism, and the principles behind electromagnetic rotation, which is the basis of the electric motor. He built the first electric motor and the first electrical transformer. He gave the famous Christmas lectures at the Royal Institution for Children, including a series called The Chemical History of a Candle that remains a masterpiece of science communication. He was offered the presidency of the Royal Society and turned it down. He was offered a knighthood and turned it down. He was offered burial in Westminster Abbey next to Newton and declined, requesting a simple grave. There's something deeply admirable about Faraday, a man who came from nothing, revolutionized physics, and never let fame or status change who he was. But Faraday couldn't express his ideas mathematically. He knew what the fields looked like, he knew how they behaved, but he didn't have the mathematical language to write them down as equations. That task fell to James Clerk Maxwell, a Scottish physicist born in 1831, the same year Faraday discovered induction. And what Maxwell did with Faraday's ideas is one of the supreme achievements of the human mind. Maxwell took Faraday's intuitive, visual concept of electric and magnetic fields and translated it into precise mathematical form. Between 1861 and 1865, he developed a set of 4 equations, Maxwell's equations, as they're now universally known, that describe everything about electricity and magnetism, how electric charges create electric fields, how moving charges create magnetic fields, how changing magnetic fields create electric fields, how changing electric fields create magnetic fields. 4 equations, and they contain all of classical electromagnetism. Every phenomenon involving electricity or magnetism, lightning, radio waves, the glow of a light bulb, the operation of a motor, the transmission of a nerve impulse, is described by these four equations. But here's the really wild part. When Maxwell worked through the math, he found that his equations predicted the existence of electromagnetic waves, self-sustaining ripples of oscillating electric and magnetic fields that would propagate through space at a specific speed. And when he calculated that speed, it came out to about 310,000 kilometers per second, which was, within experimental error, exactly the measured speed of light. Maxwell's reaction, as he wrote to a colleague, was essentially, "This can't be a coincidence. Light is an electromagnetic wave." Think about what just happened. Two seemingly unrelated things, electricity and magnetism, have been unified into a single theory. And that theory turns out to also explain light. Three phenomena for the price of one. Maxwell had done for electromagnetism what Newton had done for gravity, found the deep unity hiding behind the apparent diversity of nature. And the speed of light, this number that seemed to come out of nowhere, emerged naturally from the equations of electricity and magnetism. It wasn't put in by hand. It fell out of the math. That's a hallmark of a deep theory. It explains more than it was designed to explain. And there's something else Maxwell's equations revealed that was deeply puzzling, something we touched on when we talked about the crisis of the late 19th century. The equations gave a specific value for the speed of electromagnetic waves, and that value didn't depend on anything. It wasn't the speed relative to the source. It wasn't the speed relative to the observer. It was just the speed, a constant, built into the fabric of electromagnetism. About 299,792 kilometers per second. This troubled physicists enormously, because in Newtonian mechanics, speeds are always relative. If you're on a train doing 60 and throw a ball forward at 20, someone on the platform sees that ball at 80. Speeds add. But Maxwell's equations seem to be saying that the speed of light doesn't add. It's the same for everyone, regardless of how you're moving. That apparent contradiction between the relativity of Newtonian mechanics and the absoluteness of the speed of light was a ticking bomb sitting in the foundations of physics. It would take Einstein to diffuse it, but that's a story we'll get to soon. Maxwell died in 1879 at the age of 48, of abdominal cancer, the same disease that had killed his mother at the same age. He didn't live to see his electromagnetic waves experimentally confirmed. That came in 1887, when Heinrich Hertz, a German physicist, built an apparatus that generated and detected radio waves in his laboratory. Hertz showed that these waves traveled at the speed of light, could be reflected, refracted, and focused just like light waves, and behaved in every way exactly as Maxwell's equations predicted. The wireless age was born. Within a decade, Guglielmo Marconi was transmitting radio signals across the Atlantic. Within a century, the entire infrastructure of modern communication, radio, television, cell phones, Wi-Fi, Bluetooth, satellite links, would be built on the foundation Maxwell laid. So by the end of the 19th century, physics had two magnificent pillars: Newton's mechanics, governing motion and gravity; Maxwell's electromagnetism, governing light and electric and magnetic phenomena; and there was thermodynamics, with its deep insights about energy and entropy. The universe seemed well understood. Lord Kelvin, in a famous remark often attributed to the 1890s, supposedly declared that physics was essentially complete, that only a few small clouds remained on the horizon, a couple of minor puzzles to clean up. He was spectacularly wrong. Those small clouds were about to become hurricanes, and the two problems he was referring to, one involving the way hot objects radiate light, and the other involving a failed experiment to detect the Earth's motion through a hypothetical substance called the ether, would each lead to a revolution that would shatter the Newtonian worldview and rebuild physics from the ground up. One revolution would give us quantum mechanics, the other would give us relativity, and both would emerge in the first few years of the 20th century, from the minds of people who were young, restless, and not particularly respectful of authority. The story of these revolutions deserves to be told slowly, because they're among the most dramatic intellectual upheavals in human history. Let's start with the one that came first chronologically, and with the most unlikely revolutionary, a conservative, meticulous, order-loving German physicist named Max Planck. In the year 1900, Planck was 42 years old, a professor in Berlin, deeply respected, but not considered a radical by any stretch. He had devoted much of his career to thermodynamics, and the problem he was working on was the one Kelvin had called a small cloud, the question of how hot objects radiate light. This was the black body radiation problem, and we talked about hot objects earlier, remember, when we discussed how a piece of metal in a forge glows red, then orange, then yellow, then white as it gets hotter. Physicists had carefully measured the spectrum of this radiation, how much energy is emitted at each color, each frequency, and they had beautiful experimental data showing smooth curves that peaked at different frequencies depending on the temperature. The problem was that classical physics couldn't explain those curves. When physicists applied the laws of thermodynamics and Maxwell's electromagnetism, they got a prediction that worked at low frequencies but went catastrophically wrong at high frequencies. The theory predicted that the energy should keep increasing without limit as you went to higher and higher frequencies, into the ultraviolet and beyond, implying that every warm object should be radiating infinite energy. This was absurd, obviously, and it got a wonderfully dramatic name, the ultraviolet catastrophe. Planck tried everything to derive the correct formula using classical physics. He couldn't, and eventually, in what he later called an act of desperation, he introduced a radical assumption. He said that the tiny oscillators in the walls of a hot object can only emit or absorb energy in discrete chunks, specific, indivisible amounts he called quanta. The energy of each quantum was proportional to the frequency of the radiation, multiplied by a new constant, a tiny number that would come to be called Planck's constant, h. It was approximately 6.6 times 10 to the minus 34 joule seconds, incredibly small. But with this one assumption, the formula worked perfectly. It matched the experimental data at every frequency. Planck didn't fully believe his own assumption. He thought it was a mathematical trick, a temporary fix that someone would eventually explain using proper classical physics. Nobody ever did. What Planck had done, without quite realizing it, was discover that energy comes in lumps, that at the most fundamental level, the universe is grainy, not smooth. It was December 14th, 1900. That date is sometimes called the birthday of quantum physics. Now, to understand what Einstein did, you need to know about the crisis that was brewing. Physicists had tried to detect the ether, the hypothetical medium through which light supposedly traveled, and the most famous attempt was the Michelson-Morley experiment of 1887. Albert Michelson and Edward Morley built an exquisitely sensitive interferometer in Cleveland, Ohio, designed to detect tiny differences in the speed of light in different directions as the Earth moved through the ether. They found nothing. No ether wind. The speed of light was the same in every direction. Hendrik Lorentz and George Fitzgerald proposed that objects contract along the direction of motion through the ether, which would explain the null result. Their mathematics was correct. The Lorentz transformations would prove foundational, but their physical interpretation, tied to the ether, was about to be swept away. And then came Einstein. We've met him before in other contexts, but let me set the scene for 1905, because what happened that year is almost impossible to exaggerate. Einstein was 26, working as a patent clerk in Bern, Switzerland, because he couldn't get an academic position. He'd graduated from the ETH in Zurich, but his professors hadn't been particularly impressed. He'd skipped too many lectures, been too cocky, too independent. So he reviewed patent applications during the day and did physics on scraps of time. And in 1905, he published 4 papers, any one of which would have made a career. Together, they changed everything. The first paper explained the photoelectric effect, why light shining on certain metals ejects electrons, and why the energy of those electrons depends on the color of the light, not its brightness. Einstein's explanation was radical. Light itself comes in quanta, in packets of energy, each one carrying an energy equal to Planck's constant times the frequency. This was bolder than Planck. Planck had quantized the oscillators. Einstein was quantizing the light itself. He was saying that light, which Maxwell had conclusively shown was a continuous wave, also behaves as a stream of particles. Both things are true. This is wave-particle duality, and it remains one of the most mind-bending aspects of quantum physics. Einstein won the Nobel Prize for this work in 1921, not for relativity, which is what most people associate with him, but for the photoelectric effect. The second paper proved that atoms are real. Seriously, in 1905, there were still respectable scientists who doubted whether atoms existed or were just useful mathematical fictions. Einstein analyzed Brownian motion, the random jiggling of tiny particles suspended in water, first observed by the botanist Robert Brown in 1827, and showed that the motion could be explained quantitatively as the result of individual water molecules bumping into the suspended particles. He derived specific predictions about how far the particles should drift over time, and these were experimentally confirmed by Jean Perrin within a few years. After that, nobody seriously doubted atoms anymore. The third paper was special relativity. This is the one that dealt with the other small cloud, the failure of the Michelson-Morley experiment to detect the Earth's motion through the ether. Einstein's solution was breathtaking in its simplicity. He said, "There is no ether. The speed of light is the same for all observers, regardless of their motion." And then he followed the logic wherever it led, and it led to time dilation. Moving clocks run slow, and length contraction. Moving objects shrink in the direction of motion, and the relativity of simultaneity. Two events that are simultaneous for one observer may not be simultaneous for another. Space and time aren't fixed, absolute stages on which physics plays out. They're flexible, interwoven, affected by motion. This was a direct challenge to Newton, whose mechanics assumed absolute space and absolute time as fixed backgrounds. The fourth paper was a short addendum to the third. It contained the most famous equation in physics, E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy are the same thing, in different forms. A tiny amount of mass corresponds to an enormous amount of energy, because the speed of light squared is such a fantastically large number. This equation would eventually explain how the sun shines, by converting mass into energy through nuclear fusion, and it would make nuclear weapons possible. But in 1905, those applications were decades away. Einstein had just rewritten the foundations of physics from a patent office at 26. Now, special relativity dealt with observers moving at constant velocities. But what about acceleration? What about gravity? Einstein wasn't done. Starting around 1907, he began working on what would become general relativity, and it would take him 8 agonizing years. The key insight came early, what he later called the happiest thought of his life. He realized that a person in free fall feels no gravity. If you're falling freely, you're weightless. And that means gravity and acceleration are, in a deep sense, the same thing. This equivalence principle led Einstein to a radical conclusion. Gravity is not a force in the Newtonian sense. It's a curvature of space-time. Massive objects like the sun curve the geometry of the space and time around them, and other objects, planets, light, everything, follow the curves. The Earth doesn't orbit the sun because the sun is pulling on it with a force. The Earth orbits the sun because the sun has warped space-time in its vicinity, and the Earth is following the straightest possible path through that curved geometry. Einstein needed new mathematics to express this, the tensor calculus and differential geometry developed by Bernhard Riemann in the 19th century. And he struggled with it terribly. For 8 years, from 1907 to 1915, Einstein wrestled with the mathematics, a period he later described as the most difficult intellectual labor of his life. He sought help from his old classmate Marcel Grossmann, a mathematician at the ETH in Zurich. Grossmann introduced him to the Riemann curvature tensor, the metric tensor, the whole apparatus of differential geometry. Together, they published a preliminary theory in 1913 that was close but not right. Einstein went down wrong paths, published incorrect equations, convinced himself through a flawed argument that the correct equations were impossible. And meanwhile, David Hilbert, arguably the greatest mathematician in the world, had become interested in the problem and was racing Einstein to the finish line. The autumn of 1915 was extraordinarily intense. Einstein presented 4 papers to the Prussian Academy of Sciences on consecutive Thursdays in November, each one bringing him closer to the final answer. On November 18th, he used his still incomplete equations to calculate the anomalous precession of Mercury's orbit, and got exactly the right answer, 43 arcseconds per century. He was so excited his heart palpitated, and on November 25, 1915, Einstein presented the final, correct field equations of general relativity. He tested them immediately on a known puzzle, the tiny anomaly in Mercury's orbit that had baffled astronomers for decades. His equations predicted the anomaly perfectly. He later told a colleague that when he saw the result, his heart palpitated. General relativity was confirmed spectacularly in 1919 when Arthur Eddington's observations during a total solar eclipse showed that starlight was bent by the sun's gravity by the amount Einstein predicted, twice the amount Newton's theory would give. Einstein became an overnight global celebrity, and the theory has been confirmed again and again ever since. By the time dilation measured in GPS satellites, by the detection of gravitational waves by LIGO in 2015, by the first image of a black hole's shadow in 2019, every test, every observation has matched Einstein's predictions with extraordinary precision. But while Einstein was reshaping our understanding of gravity and space-time, the quantum revolution was accelerating, and it was producing ideas that Einstein himself would find deeply troubling, ideas about probability, uncertainty, and the nature of reality that he would spend the rest of his life fighting against. After Planck's quanta and Einstein's photons, the next great leap came from Niels Bohr, a Danish physicist who in 1913 proposed a new model of the atom. Bohr said, "Electrons can only orbit the nucleus at certain allowed distances, and when they jump between orbits, they emit or absorb light of very specific frequencies." This explained why each element has its own unique spectral fingerprint. Those sharp-colored lines you see when you heat a gas and look at it through a prism. Bohr's model worked beautifully for hydrogen, but struggled with heavier atoms, and nobody could explain why the electrons were restricted to those specific orbits. The explanation came from Louis de Broglie, a French prince who proposed in his 1924 doctoral thesis that particles of matter, electrons, protons, everything, also have wave properties. Just as light is both wave and particle, so is matter. An electron's wavelength is given by Planck's constant, divided by its momentum. For everyday objects, this wavelength is so absurdly tiny it's undetectable. But for something as light as an electron, the wavelength is comparable to the size of an atom, and it matters enormously. The allowed orbits in Bohr's model are precisely the orbits where the electron's wavelength fits perfectly around the circumference. Whole numbers of wavelengths, like standing waves on a guitar string. Quantization isn't a mysterious decree. It's a natural consequence of the wave nature of matter. Then came the full theory, arriving in 1925 and 1926 from two different directions at almost the same time. The first came from Werner Heisenberg, just 23 years old, working as an assistant to Max Born in Göttingen. Heisenberg was brilliant and impatient, and he suffered terribly from hay fever. The pollen was so bad that summer that he fled to Helgoland, a barren rocky island in the North Sea where there was almost no vegetation, and there, alone on this windswept rock, working through the nights, he developed an entirely new approach to atomic physics. He decided to throw out everything you couldn't directly observe, no electron orbits, no visualizable paths, and build a theory entirely out of measurable quantities, the frequencies and intensities of light that atoms emit and absorb. The math he ended up with involved arrays of numbers whose multiplication depended on the order. A times B did not equal B times A. He found this deeply unsettling and stayed up all night checking his calculations. At 3 a.m, when he'd confirmed the result, he was too wired to sleep and walked to the tip of the island to watch the sun come up over the North Sea. He knew he had something. When Max Born saw the work back in Göttingen, he recognized the mathematics immediately. Heisenberg had independently reinvented matrix algebra. What became known as matrix mechanics was the first complete formulation of quantum mechanics. Then, just a few months later, Erwin Schrödinger took a completely different approach. Schrödinger was older, in his late 30s, and inspired by de Broglie's matter waves. If electrons are waves, he reasoned, there should be a wave equation governing them. He derived his famous equation during what has become one of physics' most legendary retreats, a holiday in the Swiss Alps in December 1925, at a villa in Arosa, accompanied by a woman who was not his wife. History has never established who she was, but over those few intensely productive weeks, Schrödinger produced an equation that would become one of the most important in all of science. Unlike Heisenberg's abstract matrices, Schrödinger's equation looked familiar. It was a differential equation, the kind of math physicists had been using for centuries. You could picture things. You could imagine waves sloshing around. Physicists loved it. The two approaches looked completely different, but they turned out to be mathematically equivalent. Schrödinger himself proved this. Two languages for the same physics. The interpretation of this new quantum mechanics was where things got truly strange. Max Born proposed that the wave function, the central object in Schrödinger's equation, doesn't describe a physical wave. It describes probabilities. The square of the wave function at any point tells you the probability of finding the particle there if you look. Before you look, the particle doesn't have a definite position. It exists in a superposition of possibilities. Only when you measure does the wave function collapse to a single outcome. Nature, at its most fundamental level, is not deterministic. It's probabilistic, and not because we lack information, because there is no information to have. The universe genuinely hasn't decided yet until you measure. Heisenberg made this even more concrete with his uncertainty principle in 1927. You cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't about clumsy instruments or imperfect measurements. It's a fundamental feature of nature. The universe has a built-in fuzziness at small scales that no technology will ever overcome. Einstein hated this. Not the math. The math clearly worked, but the interpretation. He believed particles have definite properties whether anyone is looking or not. He believed the universe is deterministic underneath, and quantum mechanics is just an incomplete description of some deeper, more sensible reality. God does not play dice, he famously said. Bohr shot back that Einstein should stop telling God what to do. Their debate, carried on through letters and legendary confrontations at the Solvay conferences in Brussels, is one of the great intellectual battles in the history of science. Einstein would propose clever thought experiments designed to break quantum mechanics, and Bohr would find the flaw every time. By morning, Einstein would propose a new one. By dinner, Bohr would refute it. One particularly dramatic exchange came at the 1930 Solvay conference. Einstein proposed a fiendishly clever thought experiment involving a box of radiation with a clock-controlled shutter. By weighing the box before and after releasing a single photon and using E equals mc squared to calculate the photon's energy from the change in mass, you could seemingly know both the energy and the time of emission with arbitrary precision, violating the energy-time uncertainty relation. Bohr was visibly shaken. He couldn't find the flaw that evening, but by the next morning, he had it. And here's the beautiful irony. He used Einstein's own general relativity to show that the gravitational redshift, caused by weighing the box, introduced just enough uncertainty in the timing to preserve Heisenberg's principle. Einstein had been refuted by his own theory. In 1935, Einstein made his strongest argument, the EPR paper, written with Boris Podolsky and Nathan Rosen. They described a situation where two particles, created together and then separated by a vast distance, remain mysteriously correlated. Measuring one particle instantly determines the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and argued it proved quantum mechanics was incomplete. But in 1964, the Irish physicist John Bell showed that this question could be experimentally tested, and starting in the 1980s, experiments by Alain Aspect and others confirmed that quantum mechanics is right. The correlations are real. Nature really is that strange. Einstein, on this particular point, was wrong. The universe does play dice. But while the philosophical debates raged, quantum mechanics was quietly transforming the practical world in ways that would affect every person on the planet. And this is one of the things I love most about the history of physics. The way the most abstract, seemingly impractical ideas turn out to have the most profound real-world consequences. Nobody studying the energy levels of electrons in atoms in the 1920s was thinking about smartphones. Nobody working on semiconductor band theory in the 1930s was imagining the internet. Nobody theorizing about stimulated emission of radiation in 1917 was picturing fiber optic cables carrying YouTube videos across the ocean floor. But that's how it works. Understanding the fundamental laws of nature gives you power over nature, especially when, you weren't looking for that power. The applications come later, sometimes decades later, and they come in ways nobody predicted. The theory explained why some materials conduct electricity and others don't, through the quantum mechanics of electron energy bands in solids. It explained how to manipulate semiconductors by doping them with impurities, creating the p-n junctions at the heart of every diode and transistor. The transistor itself, invented at Bell Labs in 1947 by William Shockley, John Bardeen, and Walter Brattain, is a quantum mechanical device through and through. The entire electronics revolution, computers, smartphones, the internet, everything built on integrated circuits, rests on quantum mechanics. Every chip in your phone contains billions of transistors, each one a tiny quantum device switching on and off billions of times per second. And quantum mechanics didn't just give us electronics, it gave us lasers, devices based on Einstein's 1917 prediction of stimulated emission, first built by Theodore Feynman in 1960. Every barcode scanner, every fiber optic cable, every CD player, every eye surgery that reshapes a cornea, lasers, all of them. It gave us MRI machines, which work by manipulating the quantum spin of hydrogen nuclei in your body. It gave us atomic clocks, whose extraordinary precision makes GPS possible. Without quantum mechanics, the modern world simply doesn't exist. Meanwhile, on another front entirely, physicists were probing the interior of the atom and discovering a whole new layer of reality. And the story of how they did it is one of the great detective stories in science. J.J. Thomson discovered the electron in 1897 at the Cavendish Laboratory in Cambridge, using cathode ray tubes, glass tubes with most of the air pumped out, through which he passed an electric current. He found that the rays were made of particles far lighter than any atom, carrying a negative electric charge. These were electrons, the first subatomic particles ever identified. Thomson proposed the plum pudding model of the atom, imagining electrons embedded in a diffuse blob of positive charge, like raisins in a pudding. Then came Ernest Rutherford, a New Zealander who had come to Cambridge to work with Thomson and who had a genius for experimental physics and a booming voice that reportedly once set off radiation detectors in his own lab. In 1909, Rutherford and his colleagues Hans Geiger and Ernest Marsden performed the famous gold foil experiment in Manchester. They fired alpha particles, essentially helium nuclei, at an incredibly thin sheet of gold foil, and watched where the particles ended up using flashes of light on a zinc sulfide screen. Most alpha particles sailed right through, as expected, but a few, a tiny, shocking fraction, bounced almost straight back. Rutherford later said, "It was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you." The only explanation was that most of the atom is empty space, and almost all its mass and positive charge is concentrated in a fantastically tiny region at the center, the nucleus. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble on the 50-yard line. Everything you think of as solid matter is overwhelmingly empty. Rutherford's experiments had revealed the atomic nucleus, a tiny, dense core containing almost all the atom's mass. By the 1930s, physicists had figured out that the nucleus is made of protons and neutrons, held together by a new force, the strong nuclear force, that is far more powerful than electromagnetism, but acts only over incredibly short distances, about the size of the nucleus itself. Understanding this force, and the nuclear reactions it governs, would lead to both the most destructive and the most productive technologies of the 20th century. Nuclear fission was discovered in 1938, and the circumstances are a powerful reminder that science doesn't happen in a vacuum. It happens in the middle of history, with all its cruelty and contingency. Otto Hahn and Fritz Strassmann, working in their Berlin laboratory, bombarded uranium with neutrons, and found, to their astonishment, barium in the products. That made no sense. How could firing a tiny neutron at a uranium nucleus produce barium, an element with barely half the atomic mass? They couldn't explain it, but Lise Meitner could. Meitner had worked alongside Hahn for 30 years. She was his equal in every sense, arguably his superior in theoretical physics. But she was Austrian, and she was Jewish, and in 1938, she had been forced to flee Nazi Germany, escaping to Sweden with little more than the clothes on her back and 10 marks in her pocket. When Hahn wrote to her about the puzzling barium results, Meitner and her nephew Otto Frisch worked out the explanation during a Christmas visit in the Swedish countryside. The uranium nucleus was splitting in two, fissioning, and the energy released matched what Einstein's E equals mc squared predicted for the mass difference. Meitner is one of the most unjustly overlooked figures in the history of physics. She did crucial work on the theory of fission, but she was passed over for the Nobel Prize, which went to Hahn alone in 1944. She never received the recognition she deserved during her lifetime. The discovery that a uranium nucleus could be split by a neutron, releasing enormous energy, and more neutrons that could split more nuclei in a chain reaction. This was both a scientific breakthrough and an existential crisis. Within 7 years, that chain reaction had been harnessed into both a nuclear reactor and a nuclear bomb. The Manhattan Project, led by J. Robert Oppenheimer, was one of the largest and most consequential scientific endeavors in history. At its peak, it employed more than 125,000 people across secret facilities in Los Alamos, New Mexico, Oak Ridge, Tennessee, and Hanford, Washington. Oppenheimer himself was a fascinating, tortured figure, a theoretical physicist who could read Sanskrit, who had studied Hindu philosophy, who wrote poetry, and who was asked to organize the practical engineering of a weapon of unprecedented destructive power. He recruited many of the greatest physicists of the era, Enrico Fermi, who had built the first controlled nuclear reactor under the bleachers of a squash court at the University of Chicago in December 1942, Hans Bethe, who had figured out how nuclear fusion powers the sun, Richard Feynman, still in his 20s and already showing the irreverent genius that would make him a legend. The theoretical and engineering challenges were immense. They had to figure out how to produce enough fissile material, how to assemble it into a device that would achieve a supercritical mass rapidly enough to produce an explosion rather than just fizzling, and they had to do it all under wartime secrecy. The first nuclear test, Trinity, took place on July 16, 1945, in the New Mexico desert. Oppenheimer later said that the explosion reminded him of a line from Hindu scripture, "Now I am become death, the destroyer of worlds." 3 weeks later, atomic bombs were dropped on Hiroshima and Nagasaki. The physics that had begun with curiosity about how the world works had produced the most devastating weapons in history. But nuclear physics also gave us nuclear power, controversial, complicated, but capable of generating enormous amounts of electricity without burning fossil fuels. And it gave us nuclear medicine and radiocarbon dating and our understanding of how stars shine. The sun, and every star you see, is a nuclear furnace, fusing hydrogen into helium deep in its core, converting a tiny fraction of mass into energy, according to Einstein's E equals mc squared. The same equation that makes bombs possible makes stars possible. Physics doesn't judge, it just describes. One of the most brilliant physicists to emerge from the war years was Richard Feynman, who had worked on the Manhattan Project as a young man and went on to develop quantum electrodynamics, QED, the quantum theory of the electromagnetic force. QED is often cited as the most precise theory in all of science, and Feynman's approach to it was characteristically creative. He invented a visual shorthand, Feynman diagrams, that turned impossibly complicated calculations into something almost like cartoons. Lines representing particles, vertices representing interactions, and simple rules for translating the pictures into mathematics. These diagrams are still the standard tool of particle physics today. Feynman shared the 1965 Nobel Prize with Julian Schwinger and Shinichiro Tomonaga, who had independently developed equivalent formulations. Feynman was also one of the great science communicators of the 20th century. His lectures at Caltech, published as the Feynman Lectures on Physics, remain among the best introductions to the subject ever written. He had a gift for making the complex feel simple without ever dumbing it down. After the war, physics entered what might be called its industrial age. The war had demonstrated that physics could change the world, for better and for worse, and governments poured money into research on an unprecedented scale. Particle accelerators grew larger and more powerful. New detectors were developed that could track subatomic particles with exquisite precision, and physicists turned their attention to an even deeper question. What are the truly fundamental building blocks of matter? Protons and neutrons aren't elementary. They're made of smaller things. Through the 1950s and 1960s, particle accelerators kept finding new particles, a bewildering zoo of mesons, baryons, hyperons, resonances. The physicist Willis Lamb joked that the Nobel Prize should go to the physicist who didn't discover a new particle that year. It was a mess. But gradually, a pattern emerged. In 1964, Murray Gell-Mann and George Zweig independently proposed that all these particles were made of a small number of truly fundamental constituents, which Gell-Mann playfully named quarks, a word borrowed from James Joyce's Finnegan's Wake. There are 6 types of quarks in 3 generations, with names like up, down, charm, strange, top, and bottom. Protons are made of 2 up quarks and 1 down quark. Neutrons are 2 down quarks and 1 up quark. The strong force that binds quarks together is carried by particles called gluons, and the theory describing it, quantum chromodynamics, is one of the pillars of the Standard Model of particle physics. The Standard Model, assembled piece by piece through the second half of the 20th century, is one of the most successful theories in the history of science. It describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, along with all the known elementary particles, 6 quarks, 6 leptons, including the electron, and 3 types of neutrinos, the force-carrying bosons, photons, gluons, W and Z bosons, and the Higgs boson, which gives particles their mass through the Higgs mechanism. The prediction and discovery of the Higgs boson is itself a remarkable story that captures something essential about how modern physics works. Peter Higgs, a shy, unassuming British physicist at the University of Edinburgh, proposed the mechanism in 1964, along with several other theorists working independently: François Englert and Robert Brout in Brussels, Gerald Guralnick, Carl Hagen, and Tom Kibble in London. The idea was that empty space is permeated by an invisible field, the Higgs field, and that particles acquire mass through their interaction with this field. It's often described with an analogy. Imagine a room full of people at a party. A nobody can walk through easily, like a massless photon passing through the Higgs field without interacting. But a celebrity entering the room gets surrounded by admirers, slowed down, made heavier. That's how a massive particle interacts with the Higgs field. The analogy is imperfect, but it captures the basic idea. The particle associated with this field, the Higgs boson, was predicted to exist, but it was incredibly difficult to detect because it's unstable, decaying almost instantly into other particles. Finding it required a machine of almost absurd ambition. CERN's Large Hadron Collider, a 27-kilometer ring of superconducting magnets, buried 100 meters beneath the Swiss-French border near Geneva. The LHC accelerates protons to 99.9999991% of the speed of light and smashes them together, producing conditions that haven't existed since a trillionth of a second after the Big Bang. It took thousands of scientists from dozens of countries, over a decade of construction, and billions of dollars. On July 4, 2012, the two main detector teams, ATLAS and CMS, announced they had found it. Nearly half a century between prediction and confirmation. Peter Higgs was in the audience that day. He wept. He and François Englert shared the 2013 Nobel Prize. Robert Brout had died the previous year. And the particle behaved exactly as the theory predicted. The standard model is precise. It has been tested to extraordinary accuracy. Quantum electrodynamics, the part dealing with electromagnetism, predicts the magnetic moment of the electron to about 1 part in 10 trillion, which is the most precise prediction in all of science. And yet, physicists know the standard model is incomplete. It doesn't include gravity. It doesn't explain dark matter, the mysterious substance that makes up about 27% of the universe's mass-energy content. The evidence for dark matter goes back to the 1930s, when the Swiss astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast to be held together by the visible matter alone. Something unseen was providing extra gravity. In the 1970s, the American astronomer Vera Rubin and her collaborator Kent Ford confirmed this at the scale of individual galaxies. Stars at the outer edges of galaxies orbit just as fast as stars near the center, which only makes sense if there's a huge halo of invisible mass surrounding each galaxy. Dark matter is detectable through its gravitational effects, but otherwise invisible. It doesn't emit light, doesn't absorb light, doesn't interact with normal matter through the electromagnetic force. It doesn't explain dark energy, the even more mysterious something that makes up about 68% of the universe and is causing the expansion of the cosmos to accelerate. Ordinary matter, the stuff you and I and the stars are made of, accounts for a mere 5% of everything. We are a minority ingredient in our own universe. And here's something worth sitting with for a moment, because it connects back to the whole arc of our story. The Big Bang itself, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since, is a prediction that came directly from Einstein's general relativity. Alexander Friedmann, a Russian mathematician, showed in 1922 that Einstein's field equations naturally describe an expanding or contracting universe. Georges Lemaitre, a Belgian priest and physicist, independently reached the same conclusion in 1927 and went further, proposing that the universe began from what he poetically called a primeval atom. Einstein himself resisted the idea. He added a cosmological constant to his equations, specifically to keep the universe static, which he later called his greatest blunder. But the evidence piled up. Edwin Hubble's 1929 observations showed that galaxies are receding from us, and the farther away they are, the faster they're going. The universe is expanding, and in 1965, Arno Penzias and Robert Wilson at Bell Labs accidentally discovered the cosmic microwave background radiation, a faint, uniform glow of microwaves coming from every direction in the sky, corresponding to a temperature of about 2.7 degrees above absolute zero. This is the afterglow of the Big Bang itself. Light emitted about 380,000 years after the universe began, when the cosmos had cooled enough for atoms to form and for light to travel freely for the first time. That light has been traveling through space for almost 14 billion years, stretched by the expansion of the universe from the visible into the microwave range. You can tune an old analog television to an empty channel and see static. About 1% of that static is the cosmic microwave background. You're looking at the oldest light in the universe, a snapshot of the cosmos as an infant. And speaking of gravitational waves, that detection by LIGO in September 2015 deserves a moment of its own, because the engineering behind it is almost unbelievable. LIGO consists of two L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana, each with arms 4 kilometers long. A laser beam is split and sent down both arms, bounces off mirrors at the ends, and recombines. If a gravitational wave passes through, a ripple in space-time caused by something like two black holes merging, it stretches one arm and compresses the other by an almost inconceivably tiny amount. How tiny? LIGO can detect a change in the length of its arms of about 1/10,000th the diameter of a proton. That's like measuring the distance to the nearest star to an accuracy of the width of a human hair. The signal they detected on September 14, 2015, came from two black holes, each about 30 times the mass of the Sun, spiraling into each other 1.3 billion light-years away. The waveform matched Einstein's predictions perfectly. A century-old theory, tested in the most extreme conditions nature can produce, and it passed. Kip Thorne, Rainer Weiss, and Barry Barish shared the 2017 Nobel Prize for the detection. And then, in 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87, 6.5 billion times the mass of our Sun. The image was reconstructed from radio data collected by a network of telescopes spanning the entire globe, effectively creating an Earth-sized radio dish. The glowing ring of superheated gas, the dark shadow in the center, where light cannot escape. It looked precisely like what general relativity predicted. A century of theory, from Schwarzschild's wartime calculation to Penrose's trapped surfaces to Hawking's radiation, and there it was, staring back at us from 55 million light-years away. The story of dark energy begins with an observation made in 1998 that shocked the physics community. Two teams of astronomers, studying distant supernovae to measure the expansion rate of the universe, discovered that the expansion isn't slowing down, as everyone expected. It's speeding up. Something is pushing the universe apart, faster and faster, and nobody knows what it is. Einstein had actually predicted something like this back in 1917, his cosmological constant, a term he added to his field equations to keep the universe static, which he later called his greatest blunder. But it turns out the universe actually does have something like a cosmological constant, and it dominates the entire energy budget of the cosmos. Einstein's blunder may have been one of his deepest insights. There's another deep mystery worth mentioning: the matter-antimatter asymmetry. For every type of particle, there exists an antiparticle with the same mass but opposite charge. When a particle meets its antiparticle, they annihilate each other in a burst of pure energy. The equations of the Standard Model treat matter and antimatter almost symmetrically, which raises a troubling question: why is the universe made of matter at all? In the earliest moments after the Big Bang, matter and antimatter should have been created in equal amounts, and they should have annihilated each other completely, leaving nothing but radiation. But they didn't. For every billion antimatter particles produced, there were about 1,000,000,001 matter particles. That tiny excess, 1 part in a billion, is everything. Every galaxy, every star, every planet, every person exists because of that minuscule asymmetry. We know it happened, but we don't fully understand why. Something in the laws of physics slightly favors matter over antimatter, and finding the precise mechanism is one of the major goals of particle physics experiments around the world. And then there's the question that looms over everything, the great unfinished business of physics. How do you reconcile general relativity, which describes gravity as smooth curvature of space-time, with quantum mechanics, which describes the other forces as quantized exchanges of particles? Both theories are spectacularly successful in their own domains, but they are fundamentally incompatible. General relativity is smooth and continuous. Quantum mechanics is discrete and probabilistic. When you try to combine them, when you ask what happens at the center of a black hole, or at the very first instant of the Big Bang, where both quantum effects and gravity are overwhelming, the math breaks down. You get infinities. Nonsense. The theories refuse to cooperate. Finding a theory of quantum gravity, something that unifies general relativity and quantum mechanics into a single coherent framework, is the holy grail of modern theoretical physics. String theory is perhaps the most ambitious attempt. It proposes that the fundamental entities aren't point-like particles, but tiny vibrating strings of energy, and that the different particles we observe are just different vibrational modes of these strings, like different notes on a guitar. String theory requires extra dimensions of space beyond the 3 we experience, typically 10 or 11 total, and these extra dimensions are curled up so small we can't detect them directly. The mathematics is extraordinarily beautiful and has produced deep insights into both physics and pure mathematics. But after more than 4 decades of development, string theory has not yet made a single testable prediction that has been experimentally confirmed. It remains a work in progress, brilliant, tantalizing, and unproven. There are hints from multiple directions that space and time might emerge from something more fundamental, from quantum entanglement, perhaps, or from information-theoretic principles. The physicist Juan Maldacena discovered in 1997 a remarkable correspondence, the ADS-CFT correspondence, suggesting that a theory of gravity in a particular kind of spacetime is exactly equivalent to a quantum theory without gravity living on the boundary of that spacetime. It's as if the 3-dimensional world inside a room is entirely encoded on its 2-dimensional walls. This is related to the holographic principle, and it's one of the deepest and strangest ideas in modern theoretical physics. Loop quantum gravity is another approach, which tries to quantize spacetime itself, suggesting that space at the tiniest scales isn't smooth, but is made of discrete chunks, tiny loops, woven together like a kind of quantum fabric. It's mathematically rigorous and doesn't require extra dimensions, but it too faces enormous challenges and lacks experimental confirmation. The honest truth is that we don't know which approach, if any, is on the right track. And there's something beautifully humbling about that. After 4 centuries of astonishing progress, from Galileo's inclined planes to LIGO's gravitational wave detectors, from Newton's apple to the Higgs boson, physics has brought us to a frontier where the deepest questions remain open. What is spacetime really made of? Why is there something rather than nothing? What happened before the Big Bang? Or is that question even meaningful? Are there other universes? Is information truly conserved, even in a black hole? Why do the fundamental constants of nature have the values they do? These questions sit at the edge of what we know, and it's worth pausing here, as you lie in the dark, to appreciate just how extraordinary the journey has been. Every major advance in physics has come from someone refusing to accept the conventional wisdom, refusing to stop asking why. Galileo refused to accept that heavy things fall faster. Newton refused to accept that the heavens and the earth follow different rules. Faraday refused to accept that a blacksmith's son couldn't do science. Maxwell refused to accept that electricity and magnetism were unrelated. Planck refused to give up on the blackbody problem, even when his own solution horrified him. Einstein refused to accept that the speed of light needed an ether to propagate through. Bohr refused to accept that classical physics could explain atoms. And at each step, the answer turned out to be stranger and more beautiful than anyone expected. And here's the thing that I find most remarkable, most comforting, most worth carrying into sleep. Every piece of physics we've talked about tonight, every law, every equation, every principle, is active right now, in this room, in your body. Gravity is holding you in your bed, described by Einstein's field equations curving space-time around the Earth beneath you. Electromagnetism is holding your atoms together, keeping the molecules of your body intact, transmitting signals through your nerves. The strong nuclear force is binding the quarks inside the protons and neutrons inside the nuclei of your atoms. The weak nuclear force is mediating certain radioactive decays happening in trace elements in your body right now. Thermodynamics is governing the flow of heat from your body into the air around you. Quantum mechanics is determining the energy levels of every electron in every atom you're made of. You are, in a very literal sense, all of physics happening at once. The same gravity that bends starlight around distant galaxies is curving space-time beneath your mattress. The same electromagnetic force that powers a supernova is firing your neurons. The same quantum mechanics that explains the color of a nebula explains the color of your eyes. The universe has been running these laws for about 14 billion years, give or take. Stars have formed, burned, exploded, and scattered their atoms across space. Some of those atoms found their way into a cloud of gas that collapsed to form our sun and its planets about 4.5 billion years ago. Some of those atoms became the Earth. Some became you. The carbon in your bones was forged in the core of a star that died before our solar system existed. The iron in your blood was created in the final moments of a supernova, an explosion so violent it briefly outshone an entire galaxy. You are made of star stuff, as Carl Sagan liked to say, and every atom in your body has a history written in the language of physics. Fusion reactions, electromagnetic cascades, quantum tunneling, gravitational collapse. And right now, those atoms are doing exactly what the laws of physics say they should. Electrons are occupying their quantum states. Chemical bonds are holding your molecules together. Heat is flowing, entropy is increasing, time is passing, measured by atomic clocks, somewhere to a precision of 1 second in 15 billion years. The whole magnificent machinery of the universe is ticking along, quietly, reliably, the same way it has since the beginning. We understand so much of it now. Not everything, maybe not even most of it, if dark matter and dark energy are any indication, but enough to land spacecraft on comets, to detect ripples in space-time from merging black holes 1 billion light-years away, to build machines that manipulate individual atoms, to see the afterglow of the Big Bang itself in the faint microwave radiation that fills every cubic centimeter of space. And still, at the deepest level, the universe keeps its secrets. What is mass, really? What is time? Why does anything exist at all? These questions are still open, still being worked on, still driving brilliant and stubborn people to spend their lives chasing answers. Somewhere right now, a graduate student is staring at equations on a blackboard, trying to make quantum mechanics and gravity talk to each other. Somewhere, an experimentalist is calibrating an instrument that might detect dark matter particles for the first time. Somewhere, a theorist is playing with a new idea about the nature of space-time that might be brilliant, or might be wrong, or might be both. And that's the thing about physics that makes it so endlessly fascinating. It's never finished. It never closes. Every answer opens new questions. Every solution reveals new mysteries. Newton thought he was describing the final truth, and Einstein showed there was a deeper layer. Einstein thought quantum mechanics must be incomplete, and experiments showed it wasn't. Whatever we believe now, some of it will turn out to be an approximation of something deeper still. And that's not a failure. That's the process working exactly as it should. Each generation peels back another layer, and the universe, far from becoming simpler, becomes richer, stranger, and more wonderful. So let that settle over you now. Let the names fade. Galileo, Newton, Faraday, Maxwell, Planck, Einstein, Bohr, Dirac, Feynman. Let them blur into a quiet chorus of people who spent their lives trying to understand, and who passed that understanding on to us. Let the equations dissolve. Let the numbers go. What remains is just this. The universe has rules, and they're knowable, and the knowing of them is one of the greatest things our species has ever done. And those rules are holding you right now, gently, reliably, the way they've held everything, everywhere, since the beginning. Gravity pressing you softly into the mattress, electromagnetism keeping you whole, quantum mechanics running quietly in every atom, the deep machinery of the cosmos, doing what it does, the way it always has, and you, lying here in the dark, made of those same atoms, governed by those same laws, part of the same story that started 14 billion years ago and will continue long after all of us are star stuff again. That's a good thing to carry into sleep. The universe is vast and old and strange and beautiful, and you are part of it. Every atom, every heartbeat, every breath. Rest well. The physics will still be running in the morning.